Welcome to AP Chemistry at Hononegah High School. I'm Brian Brown, and today we'll be looking at the icebox practice problem. So I got a short movie that'll walk you through in case you had any questions. Here's a typical example of a problem we could use icebox for. Sulfuryl chloride, which is SO2Cl2, a highly reactive gaseous compound when heated, decomposes in the following conditions. Now notice they tell us that decomposition is endothermic, which may or may not be at all useful in the problem. But they also tell us the mass of the SO2Cl2 that we start with. And they say it's placed in an evacuated 1.0 liter bulb and raised to a temperature of 375 K. So that's what they're giving us as our initial conditions. And in A, they say, what would the pressure be in atmospheres in the bulb if no dissociation of SO2Cl2 gas occurred? So basically, what is going to happen if I put this amount of SO2Cl2 in the bulb and it hasn't done anything yet? So we're looking really at our initial conditions of pressure. So if we have all SO2Cl2 under these conditions, what's its pressure going to be? Well, what kind of problem is that? Well, that's not icebox. So when we're actually going to calculate what's happening in A here, all we're really doing is a PV equals nRT problem. So if we know that for any ideal gas, PV equals nRT, if I want to find out the pressure, that would equal nRT over V. Now, when you look at the initial given information, they tell us the mass. Well, if I know the molar mass of SO2Cl2, which I can add that up off the periodic table and get 135.1 grams per mole, and I know that my temperature is this, I know my volume is this, it looks like I've got pretty much everything I need. So I can use the mass and the molar mass to calculate my N. So that's literally going to be 3.509 grams over 135.1 grams per mole. That would give me my number of moles. I need my R value here, which is 0.08206 liter atmospheres over mole kelvins. I know my temperature, my T is 375 K. And that is all over the volume, which is 1.00 liters. So really, I just solve, and I can get my pressure. So the answer to A, once I do my math here to 3 sig figs based upon my numbers, I get 0.799 ATMs. So my original pressure here of this substance is going to equal 0.799 atmospheres. So that is answer A. Now, when I get to B, I'm not doing a PV equals nRT problem anymore. Now it's talking about being at equilibrium and calculating partial pressures. Well, in order to do that, I really have to set up my icebox problem. So when we go to B, which is asking this question, we really start with our icebox situation. Remember, the first thing you do in icebox is you write the reaction, and then you set up your icebox with your reactants and products as the columns. And then we go through and we take stock of what we got. Now it tells me my total pressure is 1.43 ATMs. So at equilibrium, I would have these pressures here, my bottom 3 boxes. So really, those bottom 3 boxes are going to give me my pressures of my individual gases. So in the end, that's really what I'm trying to find is those partial pressures. Well, they tell me flat out that they're going to add up to 1.43 atmospheres. So that's something that I know given the problem even before I set up my icebox table. Now, based upon the problem, remember I threw that solid in. So it had a pressure of 0.799 ATMs. So that's my initial information. So initially I had all SO2Cl2, so I didn't have any of these. So they're going to be at 0 ATMs of pressure. Now remember change, that's where we're looking at our stoichiometry here. Since we have all reactants, over time the reactant pressure is going to drop. Now we don't really know by how much because we don't have any way of calculating that simply from pulling it out of the problem. So all I really know is it's going to go down by some amount. I'm going to call that X. But based upon my stoichiometry, I know these two are both going to go up by X. And remember, initial plus change equals your equilibrium conditions. So I know this is going to be 0.799 minus X. This is going to be X, and this is going to be X. And I know those three things have to add up to 1.43 ATM. So really what I have here is an algebra problem. This plus this plus this equals 1.43 ATMs. So once I do my algebra here, I'm going to get 0.799 plus X equals 1.43. Solve for X, and I'm going to determine that X ends up equaling 0.63 1, which I round to tenths, or I should say hundredths, 2 decimal places. So technically I get 0.631 when I take uh, my 1.43 minus 0.799. But I know for reported sig figs, that's actually going to equal 0.63 ATMs. Now, that's what X equals. So I know my pressure of SO2 equals that. And I know my partial pressure of Cl2 equals that. And all I really need to do to calculate my partial pressure of my SO2Cl2 is to take 0.799 minus my 0.631, which should be rounded to there. And that's going to give me 0.17 ATMs after I do my subtraction and round to correct sig figs. So that's my answer to B. I know these two things are going to have a pressure of 0.63 ATMs, and I know this is going to have a pressure of 0.17 ATMs. And that answers my partial pressure question. Now, in the next problem, or in the next question, it asks us to calculate a Kc or a Kp. Now, one of the things I didn't do, which I normally like to do immediately upon writing my icebox table, is I didn't write my Kc or Kp expression. Now, since I'm dealing with pressures, I think it's easier to go with a Kp here. So my Kp is going to equal SO2. Now, since I'm talking about Kp, it's pressure, so I don't put it in brackets, raised to the power of its coefficient, which is to 1 times, oops, C. Let me clean that up. Cl2 over the concentration, which in this case would be pressure, so not concentration, but I'm not going to put brackets. I'm going to put parentheses of SO2Cl2. So normally I would write that here. Now, did I really need that for calculating any of this stuff? No, which is why I didn't put it there in that case. But I think once you put your K table, it's always a good idea to write that, because when you get to the next problem, that's exactly what we're dealing with. It says calculate the Kc or Kp. Well, like I said, I'm going to go with Kp because that's the easier one to do here. I know my Kp expression equals this. Now, in my last problem, I figured out that both SO2 and Cl2 were both 0.63 ATMs. So that squared is going to equal, or I should say over 0.17 ATM, which is my pressure at equilibrium of my SO2Cl2. Is going to equal my Kp. So when I plug my numbers in and calculate, I end up with 2.3 if I go to 2 sig figs. Now, normally with K expressions, we don't write units, but in this particular 1983 problem, they ask for R and specify units. Well, ATM squared over ATM, that's just going to cancel to ATM. But this is something you are like never going to do in normal problems. They just specifically ask for it. So you'd say 2.3 and the units of atmospheres. And that's a typical example of an icebox problem.